is Analysis of Time Series, Chapter 3, Stationarity, White Noise, and some basic time series models. So we're going to start off with concepts of stationarity, which we're going to do. We've mentioned stationarity before. We're going to look at it in a little more detail now. And we're going to look at models of white noise, which are stationary and are building blocks of many other important time models. And then we'll move on to looking at some of those models. Here's a definition of weak and strong stationarity. So weak stationarity is to do with the mean and covariance. So if the mean is stationary, so the mean is constant through time, and the covariance is stationary, so the covariance between two time points is just a function of the lag, then the process is called weak stationary or second order stationary. There's a stronger definition. You might guess if that's called weak stationary, there's something called strong stationary. Strong stationary is when all joint distributions are invariant to shifts in time. That's also called strictly stationary. Now, strong stationary means that if you have any collection of times, then the joint distribution should be the same as the joint distribution if you shift by any time tau. When we have discrete time points and they're equally spaced, then thinking about a time shift is equivalent to thinking about a lag shift. So then we'll say that yn1 through ynk has the same joint density function as yn1 plus h through ynk plus h for any lag h. And here is strict stationarity written in terms of densities. So that's just the joint density of yn1 through ynk is the same as the joint density of yn1 plus h through ynk plus h. Strict stationarity implies weak stationarity. If the distributions are fully shift invariant, then their moments should be fully shift invariant. You can try and write something down to convince yourself of that if you want. What I want to think about now is how, in practice, we would look at some data and see whether a weak stationary model is appropriate for time series. And let's see. Well, the first thing that we're probably going to want to do is we would plot the data. Right, and a trend. Let's say evidence for a trend. Evidence for a trend or variations in variability through time are evidence against weak stationarity. And then to be more constructive, we can calculate the sample mean and sample ACF over different time intervals. And check they look the same, look similar. These are informal checks, but these are the starting things to do. Now things get a little more difficult if you want to assess whether a strict stationary model is appropriate for a time series data set. And this is not really very practical. This is impractical there are too many things to check. We can't really we cannot check all distributions are stable through time. And then let's think about that. We can check let's say some moments are stable through time. And but that is weak stationarity. That may be one reason why strong stationarity is generally more of a theoretical tool than a practical one. Now, stationarity plays a big role in time series analysis. And so it's worth thinking whether real time series tend to be well modeled as stationary. And I think it's kind of curious that many time series have trend or other evidence for non-stationarity. Well, so if that's the case, why do so many models have stationarity if the data doesn't? And the basic reason is because stationary models have fewer parameters and are easier to estimate, easier to fit. So what we tend to do in practice we look for ways to transform models to stationarity, and then that's if we find a relatively simple way to make the data look stationary, then we can use these simpler models and get some traction on what's going on. Okay, so here's a kind of, I think, a thought-provoking example. You can look at these two time series and you can ask whether a stationary model is appropriate for either or both of the time series. And I think for X, you could say that it looks like it has a trend. let's see. Here we go. Or possibly like this, you know, one wouldn't. It's hard to know what's trend and what's variation around a trend, but if you looked at that data and you tried to model it without a trend, then people might be surprised. Let's say Y looks more stationary. Y looks more appropriate for a stationary model. But then there's a little catch, which is that X is just the first 50 points of Y, and the moral of that is that whether data looks stationary depends on the time scale. Can depend on the time scale. There you go. So next time you're trying to look at a time series and think whether it looks stationary, think whether you would still make that conclusion if you could observe it for a whole lot longer. Now, we're going to look at the white noise model now, which is not just stationary, but stationary and uncorrelated. So here's our definition. A time series model epsilon 1 to n, which is weakly stationary, mean zero, and covariance that is sigma squared at lag 0 and 0 at any other lag, is white noise with variance sigma squared. Now, this is just IID errors in the standard statistical framework. It has many things have a special name in time series, partly because time series is an old discipline. And so we call this white noise in time series. Noise because there's no pattern, like random noise. If you listen to a realization of white noise as an audio file, you'd hear just static sound. And that's because it turns out when you have uncorrelated errors like this, all frequencies equally represented. Thinking about the sound naturally maps you to the frequency domain because your ear hears frequencies. And this will become clear when we do frequency domain analysis of time series. And signal processing, which is a lot to do with sending and receiving signals on noisy channels, was some motivation for early time series analysis. So that's where the language came from. So a basic example of white noise is Gaussian white noise. So our definition of white noise doesn't tell you a concrete distribution that it has to have. There can be many different ways to have those first two moments, uncorrelated, mean zero, constant variance. So if you want, say, to get a likelihood or to do a simulation, you need a concrete instance of white noise. And the most common is Gaussian white noise, where you just have IID, that's independent identically distributed normal random variables, mean zero, variance sigma squared. This satisfies that definition of white noise. It's Gaussian white noise. In order to understand the definition of white noise, it's interesting to look at some examples that seem a little weirder, but do fit in formally with the definition of white noise. Here's binary white noise. the simplest version would be a coin flip, 1 or -1, 1 with probability a half, -1 with probability a half. That fairly clearly has mean 0, variance 1, and because it's independent, then it's necessarily uncorrelated. So the covariance is 0 if for epsilon n, m is not equal to n. You can kind of skew this so that epsilon n is 1 minus p over p with probability p and -1 with probability 1 minus p. And although if p is very small, then it's going to be -1 almost all the time and have occasional large peaks. So it might not seem so much like white noise, but formally it satisfies our definition. Now, I have one more example for you, which is, I've called it sinusoidal white noise. Epsilon n is constructed as sine 2 pi n u. So you take a single draw u, which is uniform 0, 1, and that determines the time series for all n. So this is very far from IID. In principle, once if you know epsilon 1, then you can work out u, and then you know what all the subsequent epsilons are. So it's very, very non-independent, but it is weak stationary and even white noise. And to check that, it's a kind of exercise in writing out the definitions and doing some calculus with trigonometry that you may not have done for a while, but the trigonometric functions are going to come up more when we start looking at frequency domain representations of data. And so we might as well practice messing around with some sines and cosines now. So if we want to find the expected value of epsilon n, well, we can write this out as an expectation against the density. So epsilon n is sine 2 pi nu, and the uniform density expectation against it is just an integral from 0 to 1 du. And then the integral of sine 2 pi nu should have a 1 over 2 pi n, and a cosine 2 pi nu evaluated from 0 to 1. And if I differentiate the right-hand side, I'll also get a minus sign that I need to deal with. So this is going to be a minus there. And when I evaluate cos 2 pi nu with u at 0 and 1, these two things are going to be different by a multiple of 2 pi. So the cosines are going to be the same. In fact, always 1. And so their difference is going to be 0. So this is 0. And if I want to check for white noise, I have to look at the covariance of epsilon m with epsilon n. And this, because we've already established their mean 0, so the covariance is the expected value of the product. And then I can just write that as an integral. I have sine 2 pi mu sine 2 pi nu du. And at that point, I have to integrate a product of signs. I have to remember the trigonometric identity that tells me how to write a product of signs as a sum. And I guess I don't remember these things anymore, so I have to go to Wikipedia or somewhere to check them up. But the formula is that the product of signs is half the cosine of the difference minus the cosine of the sum. So this becomes the integral from 0 to 1 of cosine 2 pi u and minus n minus cosine 2 pi u and plus n du. Now, if m equals n, then the first term here is cosine of 0, which is 1. And the second term, if they're not both equal to 0, is some cosine that's going to integrate to 0, as we saw before. And so if m equals n, we get that the covariance of epsilon m, epsilon n is a half. Otherwise, since for any k not equal to 0, the integral from 0 to 1 of cos 2 pi ku du is equal to 0, and that means both these terms in star are 0, and so the covariance between epsilon n is 0. Okay, there you go. I formally checked that this slightly weird process is weak stationary and is white noise. Now I want to show that this process is not strong stationary or strict stationary. And for that, we need a counterexample to the shift invariance of probability distributions that defines strong stationary. And to make progress on this, it's convenient to make this plot. So here I've plotted, on the x-axis, I've plotted the random variable u that generates the whole time series. So for a given value of u, I can read off on this graph and see that epsilon 1 is the black line, epsilon 2 is the red line, epsilon 3 is the blue line, and then I just need to find a non-shift invariant probability. And here's one. It's quite convenient to look at things like, say, if epsilon 1 is 1, then I know I'm on this line. So if epsilon 1 is 1, then I in fact know epsilon 2 is 0. So the probability that epsilon 2 is 0 given epsilon 1 is 1, this is actually 1. And now if the distributions were shift invariant, so if I had strong stationarity, this would have to be the same as the probability that epsilon 3 is 0 given epsilon 2 is 1. But if epsilon 2 is 1, that means I'm either here or I'm here. I'm gonna these are the U such that epsilon 2 is 1. So I see here that if epsilon 2 is 1, epsilon 3 is not 0. So this is in fact 0, and this is not shift invariant. Proving not strict stationary. Okay, so now we've seen some different white noises. In the next section, we are going to look at some models that can be built using white noise as building blocks.